Hello everyone, my name is Eduardo and today we'll be talking about MLOps and why DevOps solutions for short in the machine learning world. This talk will also be available, we'll be also giving this talk in person at the OSS Summit Bilbao in 2023. My name is Eduardo, I am a staff incubation engineer at GitLab and my job is to understand MLOps, to understand how that fits into GitLab, understand the users, and build features to bridge the gap between what GitLab offers and what data scientists and machine learning engineers need. I am a Brazilian. I am located in the Netherlands, and before this at GitLab, I was a data scientist and also a software engineer, an Android engineer, front end, and some others. Quick overview. First, we're going to start by, I'll start with the definitions, what is MLOps in itself. Then I'm going to go on a few examples of some communication issues I will name between data scientists and the platform teams and the rest of the company, and to explain why MLOps is there. Third, I'm gonna talk about why developing this developing with machine learning is different. Then I'm gonna give an overview of how we are tackling this problem at GitLab, and finally a quick word about LLMOps. So, in Portuguese we say, let's name the cows. And so what is DevOps and what is MLOps? DevOps, short story, is a way of people working together to reduce inefficiencies and to deploy high quality software that actually solves business problems. So it's a set of processes and tooling that we implemented over time to help us deploy actually good software that users can use and it's useful for them. And MLOps is similar. It is the same idea. It's people wanting to develop processes, develop tooling to make deployment software easily and meaningful software. The only difference is that this software includes machine learning powered features. So some or all or a small amount of features are powered by machine learning. This is the only difference. So the goal is the same. But if it was the same thing, I wouldn't be here talking to you, right? So why does MLOps exist in the first place? I'm going to show some examples of some conversations that I had in the past that I will explain them later, but just some of the examples. I was a data scientist at a large company, about 300 data scientists, 3,000 developers. And part of the data science work is set up data pipelines, and we used a tool called Uzi, which is a pipeline scheduler kind of for the Hadoop. So before Airflow was a thing, and it worked for us. It wasn't perfect, but what we did is our workflow was find a similar pipeline that worked, copy paste the definition, change as we needed, push it. And it worked. It had dependencies. We had this huge DAG of pipelines. It worked. It wasn't the best, but it worked. At some point, the platform decided that it wasn't good enough. We needed to migrate to this new service that was built on the microservice framework that users had some specific setup required. Made it hard to debug, didn't really accept the format that we used to work. It would take time to deploy, to migrate, and so on. And the long story short is that this conversation happened 5 years ago. I spoke with colleagues last month, and they're still using the old one. All of the effort that was put on the new tooling went to waste because they didn't account for the user base. They created a tool for themselves, not for the users they were talking to. They should be talking to in the first place. A second example, Jupyter notebooks are part of the data science toolbox. Because for data science, the input is important, like the code is important, but output is also important. Like the images that you generate are important, and you want to have both of them to have full context. But for software engineers, they only care about the code most of the time. So the images are the output of their code are stripped away or are not versioned on Git or whatever, but they ignore. And I have been in so many conversations where software engineers just say that notebook shouldn't be used at all, or even when GitHub released notebook tips a while ago, I read someone said that they didn't want this feature because now it makes it less of a problem for data scientists to use notebooks, because they wanted data science to move away from notebooks at all. And this won't happen. Another example, this was also with me. I was working with a smaller company, and we had just deployed a part of an ML flow of MLOps kind of like setup or stack with Kubeflow, and we were about to deploy a model. We were working on deploying models or improving the model deployment, and realized that there was no model registry. There was no way to version those models, and we approached the platform team. And we needed this, and they just said that it shouldn't be necessary because since Kubeflow is already said they are end-to-end, that means what I was needing was not necessary, because if it's end-to-end, it would be there. So that was very frustrating to deal with. Another one, and this is a rite of passage for almost all data scientists dealing with a platform team, especially when it's starting, the team is starting in a new company, is convincing the platform team that data scientists need access to production data on the dev environment. That kind of breaks the connections, all the learning. Like, what do you mean production data on the dev environment? Yes, we data scientists need production data on the dev environment. I will explain why in a moment, but there's nothing we can do. I know it's not how software engineers do, but it's how data scientists need. It's not a want, it's a need, it's a must. So you might have noticed a few of the themes here, but there are main reasons why DevOps is failing machine learning. First of all, is a failing to understand the who. Is trying to force data scientists into this a software engineering workflow into data science, when data science is different and the data scientists are different. And second, failing to understand the what. Creating software with machine learning is different than creating software without machine learning. There are fundamental differences that I'll go in a minute. So, we went through what is examples, and now why is machine learning different? The first part is the who. Let's start with the who. Data scientists are not software engineers. Let's start with that. They are not software engineers. They care about different things. They have different training. The workflow that works for software engineers might not necessarily work for data scientists. And sometimes what happens is that we have a hammer and we pretend everything is a nail, but we have a screw here. So first of all, data scientists have actually different personas even in their group. So there you have machine learning engineers, which are software engineers more specialized towards machine learning. You have researchers, people more connected to the academy, even if they're embedded into companies, they act more as a research team. You have data scientists or decision scientists, which are data scientists more focused on helping the user, helping the business make decisions, so A/B testing, causal impact, and things like that. So each one of them act differently, different workflow, different tooling. Second, code is not really a craft for data scientists. Of course, some will like coding, but software engineers, code is their craft. Data scientists, machine learning is their craft. Data analysis is their craft. Code is just a means to get there. They don't care so much about writing the best code or about the newest tooling or whatever. They just want something that works for them. They have very low tolerance towards new tooling or setting up new tooling. They prefer to use what already exists. Partly this is the reason why you have like one language which is Python. Some people use R, and the libraries are consolidating, like the ecosystem of data scientists is kind of consolidated into very small amount of libraries. So data science prefer to consolidate rather to spread out and create new stuff, own tooling. And another point is that data scientists have very, very different backgrounds. It is the most diverse group of people I've worked with in the past from background. Most of them are not computer scientists. They come from philosophy, from music, from biology, from geology, physics. The group is, the way they approach problems is very different. The training for computer science is not there for a lot of the cases as well. So even things that software engineers consider basic, like Git, might be something new to someone that comes from the academia. So there's a different set of complexities that data scientists and software engineers care about. And the second point, why is machine learning different, is the what. When you're working with regular software, when you build software, you code your logic that will take some input data and output some behavior. So the code is the logic of the developer is explicit through the code. When you code review, you don't really just look at the code. You look at the logic that the code implements, right? So this is regular software development. Like you have input, it goes through some code that has the logic that the software engineer intended to implement, and you output some behavior. For machine learning, is different. Everything starts with some data that you want to extract some logic from. You don't know if the logic exists in the data. The logic is made apparent by patterns, and you write some code to extract these patterns from the data. These patterns might or might not reflect a logic that exists there or doesn't exist. And these extracted patterns will return a model that will have some logic, that will do some logic. So even if there's no logic in the training data, the code will find something, right? And then you pass some input data to this model that will finally lead to your behavior. So if you compare to the previous version, it's like a second order over here. Instead of the logic being explicit in the code, the code is explicit. The logic is implicit in the model, in the training data, and the code extracts these patterns into the model. So this leads to a lot of challenges. First of all, extracting these patterns from the data can be very expensive. Like the pipelines for machine learning are very, very expensive. Some are simple, but some can take days. You need to use GPU. You need to use more powerful hardware. They are larger. Some machine learning models are larger than 10, 20, 30 gigabytes. So the pipelines are very different. So the code that you write to extract some pattern, they will extract some pattern, but they might be completely useless. It might be the wrong pattern because the logic is not there, or the logic is there, but the patterns don't reflect it, but it will extract some pattern and it will create a model. And then you only know if that model is useful or not when you put it in production. That's the only way for sure to see whether a machine learning model is doing what it's supposed to do. You have some metrics that you can use for sanity checks, but you only know if it's better or not when it goes to production. The patterns that you learn from data, the training data itself can get stale. So for example, if you have a recommender system, like the recommendations might change. The user might want different things now. And so you have to keep retraining this model, even if the code stays the same. So it's very common, the versioning. You have a lot of different versions of the same of the model with the same code. It just changes the training data and the hyperparameters, which are the parameters that you pass into the code. All of these three, they generate a model, and you need to keep retraining your model. The development environment requires production data. This is what I mentioned before, because the code extracts pattern, right? This is what the code does. You cannot extract a useful pattern from local data, from like the toy data. You could take the production data and create some synthetic data from the production data, but the production data is part of the pipeline. Like you need production data or something that looks like production data to create a model in the dev environment. So it's not something that we want, or like it is a must that we need to do. And another point is verifying code is hard, because all of this is probabilistic, and if it's probabilistic, it's flaky, right? So if you create a model that has I don't know, 5%, 1% error rate, or something like that, each model that you create is different, and it will result in a different thing, and it might break you might break your test, and tests are harder to implement properly with machine learning. So all of these problems arise from being different both on the who and on the what. And how is GitLab approaching this? So right now, in DevOps, a while ago, or still over there, what happened is that we started to realize, okay, we need to improve our efficiency. And what happened is a bunch of different point solution tools that solve each one a specific problem appeared. And then they didn't communicate with each other really well. Then what happened, we moved into creating standardized APIs between this tooling. But the user was still, the customer or the user was still responsible for gluing all of this tooling around. A lot of error prone, a lot of security issues. And then it came with the digital duct tape, or what I call stitchers. Some vendors that would just connect all of these different, will write the glue code for you. But each one of these different tools still had their own specific language, visual language, design language, and you had to learn all of them differently. Some use different words than others for the same thing, and it was just inefficient. Right now, MLOps is just about getting to the standardized tool chains. It's not even there yet. Some vendors are already working on the digital duct tape and connecting different tooling, but we are not even really at the standardized tool chains. So how GitLab is going, we at GitLab, we are tackling this the same way we are working on DevOps, the MLOps platform. I will just read this slide and then I'll explain later. So GitLab MLOps Platform is a single application powered by a cohesive user interface, agnostic of self-managed or SaaS deployment. It is built on a single code base with a unified data store that allows organizations to resolve inefficiency and vulnerability of an unreliable DIY toolchain. What does that mean? That means on GitLab, at the DevSecOps, we look at the whole life cycle of software development. From planning, yes, agile, everything. Planning, to create, to verify the software, to secure the software, package, deploy, monitor, govern. We create a single tool that encompasses all of this development process. And what we are doing with MLOps is looking the same way. What on create is MLOps lacking? What on plan are we lacking for MLOps? What on secure? What on govern? What are the features across the whole MLOps landscape? We're not focusing on some specific here and there. We are looking at the whole thing and seeing here in each step what is missing right now. So what we want to build for MLOps, we want to build the MLOps platform. A GitLab native experience, the same place that you work with the software engineer, the product manager, and everyone. We want the data scientists to be there as well. We want GitLab to be useful to the data science. So minimal setup. The data scientist doesn't need to set up anything. They don't need to ask a DevOps or a platform engineer to set something new. If it is on GitLab, it is available to them either on the SaaS on gitlab.com or on their self-managed instance. Connected across the platform is an important point. So it's not about vertical features. We don't want to build MLOps as a vertical thing into GitLab, like something separate. No, it has to be integrated across the features that are already there. The same language, so you don't need to learn multiple tools. You learn the same tool for your issues, for your merge requests, for your package registry, for your CI, and for your machine learning development. Everything is together. And finally, it's open source, and you're building in the open. So everything that we build is available whenever I'm working, there's some users coming in, giving feedback, and I share updates very frequently on the state, even if it's not ready, just to check in with the users if the vision is going to accord, if the features are what they want, and so on and so forth. So it's a really fun way to build. And I said a bunch of words, but what did we actually do so far? So the first feature that we've built was code reviews for Jupyter Notebooks. Like I mentioned before, Jupyter Notebooks are a very weird file type because it embeds into it, it's actually a JSON, but that embeds into it code, images as base64, HTML. It's a lot. It should be it feels like it should be a binary, but it's not, and it's a JSON file with all of this. And data scientists, they write their code, they push to Git, to a Git repository, but they cannot review that code because it's Jupyter. So what we did, we implemented a native diff between these notebooks. So you can discuss, if you push a Jupyter notebook into GitLab, you have this diff between before and after on the commit. It shows the images, it shows the code, it shows the markdown, it shows everything. You can discuss both the input and the output on GitLab itself. Zero setup by the users, so you just need to push your notebook and it will be working. This was already released in 14.5. Another thing that we've built recently is model experiments. Models, when you're training a machine learning model, you train, since it's non-deterministic, every change in parameter will have a different model with a different performance by whatever thing you're measuring performance. So data scientists need to keep track of these many different trials of their models, even when they're still developing. Like, it's not even on CI yet. They are developing locally, but they want to keep track of the different models they are creating, different versions, and the artifacts that they have. A common solution for this is Excel. Data scientists use Excel for that. And an open source tool for this is MLflow. And this is where GitLab starts to do it differently. A lot of the vendors will just provide a self-managed a managed instance of MLflow to customers as a product. So they take the MLflow, which is an open source one, and provide that one. And those are what we call them the stitchers. GitLab, we're not doing that. What we did was we built model experiments directly on GitLab on the code base. We rebuilt this feature. And so it's in the same code base, it follows the same coding standards, same security processes of GitLab. But by building this into GitLab first, you have the same UI that the rest of the tool. You don't need to learn a new UI, but it's very easy for us to have this connected now to the CI pipelines. If you create your model from a CI pipeline, we will pick it up and you already display all of the information about the CI pipeline directly in the model. If it is created from an MR, imagine that you create an MR with a change, that MR triggers the training of different models because there was a change in code and data in parameters. We will see that. You'll see that that MR created these different models. The package registry, this is built on top of the package registry. So when you save a candidate or a model candidate into GitLab, you'll be able to store your model itself into GitLab. You don't need to set up a bucket or a S3. Everything is already on GitLab without any setup by the user. This is already available both in gitlab.com and also in self-managed. So the users don't need to install anything new. They don't need to go and understand a new tooling. It's already there. They don't need to ask the platform engineer either. It's already there. User management is also through GitLab. Like a lot of this tooling, you need to connect with your LDAP service or whatever. This is already using the GitLab built-in user management through projects, through permissions, through everything. And to make it easier for data scientists, because we are aiming for minimal changes on the code as little as possible. We just want them to adopt and be able to adopt. We also provide compatibility with the MLflow client. So, like I mentioned, MLflow is a common open source tool for this. If data scientists already use what we did, we rebuilt the API into GitLab so that you can connect to GitLab from that client by just changing the URL. So almost no setup necessary. This was already released in 16.2. What we're working now is the model registry. So the model experiment is kind of like the scratchpad, and the model registry is where you save models that go into production. So we are working to understand where is package registry not enough, what are the things that we need to implement over here so that this becomes truly useful for data scientists. So larger model sizes, you need to keep better track of your metadata for models. You're gonna train a lot of different versions of the same model. How do we manage that? For example, a lot of the use cases is a lot of the software engineer, a lot of the package registry are ignorant towards what is in production. Like they just provide versions and then something else manages the version. But the data science is a little bit different, that they use the model registry to already toggle what's in production or not. So data scientists want to be able to track what's deployed or not directly from the model registry. So this is in progress. We've been developing. If you're interested in this, follow that epic to give feedback or to ask for specific features. This is very exciting. So these are the train main features. We also deployed GPU runners, so your CI pipelines can use GPU as well. So if you want to train machine learning models on GitLab, you can use the GPU runners. And yeah, the final aspect here, I'm just going to do a quick talk, a quick mention of LLMOps, which is the new thing. Remember how I mentioned that ML developing with ML is one step, like a second order step above software engineering, because it's indirect, like your logic is not really on the code, it's extracted as a pattern. LLMOps will make it even worse. Why? Because it adds an additional step. So before you had a training data and you had the code would output a model that will receive input data. Now you have an additional step in between. So you have a code that extracts patterns of a really, really large training data that will generate an LLM, which is the model. This LLM will receive a prompt. And this prompt plus LLM is what I'm calling here an app. So it is instructions of how the LLM should read the input data. And then you feed the input data from the user or from another system. So there are many levels of interactions here. Like the logic is split across all of them, and it's going to be really hard to manage this. So there are many challenges that will appear that we do not consider. For example, what's in the data, like the training data, a lot of the companies won't be the ones building the LLM themselves because it's very expensive. So you're going to have some large companies building LLMs. So you need to know what's in the data, what patterns did the code extract. You need to measure different LLMs. You need to be able to switch between different LLMs. The prompts itself are artifacts. So they need to be versioned, they need to be measured. A lot of people are going to try to change these prompts, like the product manager, the UX writer. They're not really comfortable with dealing directly in the code. And then you have, these will generate an app, the prompt and the LLM will generate an app. How does that change? How does that will work with the input data? It might be that by changing the prompt, you break the app, or the LLM, you break the app, and you need to work through that. There are other things like agents that didn't even mention here that allow you to connect traditional software with LLMs and or allow LLMs to use traditional software. And all of this is going to get really crazy. And there are a lot of challenges that we will need to work through to create the same way that we are working to build efficiencies for DevOps, and how we are working to build efficiencies for MLOps. We'll have to work to build new efficiencies for LLMOps. So a summary of what I spoke today: MLOps. Basic idea, we want to improve efficiency when developing software with machine learning. the existing DevOps solutions are not enough. Even the existing MLOps solutions are not enough. Because DevOps, because it doesn't understand how they fail to understand the who, the people who are creating these machine learning models, or like the data scientists, and the what. Machine learning is different than software engineering. MLOps solutions are also not enough because they are either point solutions, like they each one fix their own specific problem, or they are stitchers, like they glue a lot of different tools, but they don't create a unified UX across this tooling. And we at GitLab, we are working at changing this by becoming the MLOps platform. That's what I had to share today. My name is Eduardo. If you want to follow on Twitter or on LinkedIn, and yeah, thank you.